Welcome back. Well, today is lecture 24, our last lecture for Physics 1112, and it's going to be a continuation of what we did last time, the nature of the atom. We're going to start with what we developed at the end of the last lecture. We found that for an electron in a hydrogen-like atom, in other words, an atom with only one electron, with an atomic number Z, in other words, a proton with a charge of plus Ze, the electron in orbit around the atom can emit light if it starts at some upper energy level with some value of n equal to n initial. Remember, n is the number of de Broglie wavelengths in the orbit. Let me just mention that n is what we actually refer to as a quantum number. Quantum numbers are numbers that describe the quantum state that a system is in. And in this case, this quantum number tells us what orbit the electron is in. In other words, it tells us the number of wavelengths that the electron has, but it could be in the n equals 1 quantum state, or the n equals 2, or n equals 3, etc., etc. And just as an aside, when objects are in their lowest energy state, that is referred to as the ground state. If you think about back when we talked about potential energy, when something was on the ground or at ground level, we usually thought about that as our zero height. That would be where the potential energy was zero. So kind of the lowest potential energy state. Well, just in general, we refer to quantum mechanical states, or kind of a lot of other kind of systems too. When an object is in its ground state, it means it's in its lowest energy state. So the ground state in this case would be the n equals 1 state. So remember, we've got an electron going around. If it drops down from some quantum number n initial to a state with a quantum number of n final, it emits a photon. The wavelength of that photon we then derived last time to be described by 1 over lambda is Z, the atomic number, times R. Sorry, misprint there. That should be, as soon as I looked at it, I knew it was wrong. Z squared. Z squared times R times 1 over m squared minus 1 over n squared. That was the form that we had when we first looked at the wavelengths, where now m we can think of as n final, the final value of the quantum number. N is the initial value, and remember, because we're dropping from an initial value to a final value, from a higher energy to a lower energy state, n initial must be larger than n final. In other words, n must be larger than m. Okay. Also, that if it were the other way around, we'd get a negative value, and we can't have a negative wavelength. Okay, very, very good. Let's stick some numbers in here. Now, we already put in some values and figured out the wavelength for the red line of the Balmer series. Once we get the wavelength, we can always use the wavelength to find an energy. Well, if we found the energy that was emitted and going from some state to a lower state, we could use that in the reverse way to think about, well, that would be the amount of energy that it would take to go from the lower state to the higher state. How much energy would we have to put into the atom to knock that electron from a lower state to a higher state? Let's figure out one of those. So last time we figured out that for the n equals 3 to 2 transition, which was the red Balmer line, we got a wavelength of 656 nanometers. So let's ask, how much energy would it take for us to put into the atom if the electron were in the n equals 2 state, if we wanted to knock it up to the n equals 3 state? Well, that would be the same energy that is emitted when the atom goes from the n equals 3 to n equals 2. In other words, it's the energy of a photon with a wavelength of 656 nanometers. Well, what's that energy? Well, we know an energy of a photon is hf, or, in terms of the wavelength, hc over lambda. In other words, 6.63, I'll just do it in 3 sig figs, times 10 to the minus 34th joule seconds, times 3 times 10 to the 8th meters per second, divided by the wavelength, 656, times 10 to the minus 9th meters. That gives us 3.00 times 10 to the minus 19th joules. And if we want, using the conversion between joules and electron volts, remember 1 electron volt is 1.60 times 10 to the minus 19th joules, we can convert that to 1.89 electron volts. Great. What about another problem? how much energy would it take to ionize the hydrogen atom? Now, what does that mean? To ionize it means to take the electron completely off. Let's imagine we wanted to ionize a hydrogen atom in its ground state. In other words, we've got an electron in its lowest energy state, n equals 1. How much energy would it take to completely remove that electron? Well, that's kind of like taking the electron and putting it into the n equals 1's what state. We can think of it as going into the n equals infinity state. Taking that electron and taking it completely out of the atom, taking it very, very far away, that would be like thinking of it as the n equals infinity state. Well, the energy that it would take for us to remove the electron would be the same energy that the electron would give off, that the photon would give off, if the electron were to drop down from the n equals infinity state to the ground state, the n equals 1 state. So all we need to do is figure out what's the wavelength for the n equals infinity to n equals 1 transition, and then figure out what's the energy of that. Okay, well, let's try that. So, considering the n equals infinity to n equals 1 transition, putting in n equals infinity for our initial value for n and n equals 1 for the final, we have 1 over lambda equals z for hydrogen is 1 times r times 1 over 1 squared, the final value squared, minus 1 over infinity squared. Now, I know mathematicians hate writing things like this, but I'm not a mathematician, so I'll just do it. 1 over infinity squared. What's infinity squared? Well, a big number squared is a bigger number. Infinity squared is infinity. 1 over infinity is 0. So we've got 1 minus 0 is 1. So multiplying this out, we just get 1.097 times 10 to the 7th inverse meters, which gives us a wavelength of 9.12 times 10 to the minus 8 meters, or an energy, hc over lambda, of 2.18 times 10 to the minus 18th joules. Converting that to electron volts, we get 13.6 electron volts. That's the ionization energy of hydrogen, which we got from our transition equation. Now, if you've had chemistry, you might have seen that before, that's the energy it takes to remove a ground state electron from hydrogen, completely remove it from the atom. But it's also the energy that would be emitted by a photon if we had a free electron being grabbed by a hydrogen atom and bringing it down to its ground state. Very, very good. Okay, well, this approach, finding this equation, using the Bohr model of the atom, that's really just the first step in understanding the structure of the atom. We looked at a quantum mechanical restriction for an electron basically going around in a circle, in a one-dimensional orbit. But an electron really has 2 dimensions that it can move around the nucleus in a sphere, and then 3 dimensions if we include variations in the radial direction. So what happens when we take those things into account? 3-dimensional structure of an orbit. Well, we get a much more complicated result for the electron. When we think about the electron moving in all 3 dimensions, when it's got an angular part going around the nucleus kind of in the angular directions, we have to add 2 more quantum numbers. So we've got the n quantum number describing where it is radially, 2 more quantum numbers describing how it's moving around in an angular direction. And then it turns out we actually need a 4th quantum number because there's another property of the electron referred to as spin that has to be described with another quantum number. So we actually have 4 different quantum numbers to describe the quantum state of the electron. There's n, which we were talking about before, which has values of 1, 2, 3, 4, etc., etc. And that describes the radius of the orbit. We can think of it in terms of what the energy of the electron is. And then there's an L value, which tells us what the angular momentum of the electron is. But it is limited to what value it has for n. L can have values from 0 up to n minus 1, but also only integer values. So if n is 3, then L could be 0, 1, or 2, up to 3 minus 1. Then m sub L, that's a quantum number that tells us the direction of the angular momentum. So not only is the value of the angular momentum restricted, but the direction of that angular momentum is restricted. m sub L can only have values, again integer values, from minus L to plus L. And then the spin quantum number can only ever have two possible values of plus or minus 1/2. So that's an intrinsic problem, of an intrinsic quality of the electron itself. So let's just think about what kind of values these quantum numbers can have. Let's say n equals 1. If n equals 1, L can only go from 0 to 1 minus 1, which is 0, so L can only be equal to 0. M sub L can only go from minus 0 to 0, well that's just 0, so M sub L can only have a value of 0, and then M sub S can be plus or minus 1/2. Well, an electron in this state, we refer to this as the 1s state. The zero angular momentum state, we call that an S state. So that's an electron in a 1s state. And we can have two electrons in that state because there are two values for the spin quantum number. There's a very important thing here called the Pauli exclusion principle, which states that no electron can have the same set of quantum numbers as another electron. So we can only have one electron with any specific set of these values. Remember, there are two values for the spin quantum number, so we can have the same value of n, m, l, and m as m sub L, as long as the m sub S value are different for the two of them. And then what about the n equals 2 possibility? Well, for n equals 2, L could be 0 to anywhere from 0 to 2 minus 1, which is 1. So either 0 or 1. So L could be 1 or 0. If L is 1, m sub L could be negative 1, 0, or positive 1. And if L equals 0, m sub L can only be 0. And then for any of these, m sub S could be plus or minus 1/2. The n equals 2, L equals 1 state, L equals 1 states are called P states. So this is the 2p state. And then n equals 2, L equals 0, that's the 2s state. For n equals 3, we could have L equals 2, 1, or 0, and when L equals 2, m sub L could be minus 2, minus 1, 0, plus 1, plus 2, etc., etc. And then the L equals 2 states are called the D states. So this is the 3D state. And there we go. You can go on more and more. But I just want you to notice that if you've had chemistry before, you might have seen this, that you can have two electrons then in the 1s state. You can have 1, 2, 3, 4, 5, 6 electrons in the 2p state, with 2 more in the 2s state, making a total of 8 electrons in the 2 state. If you've ever heard of the octet rule, there we go, 8 electrons can fit in the n equals 2 state. And then in the D state, the 3D state, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 for the two values of m sub S. We can put 10 electrons in the 3D state, then 8 more in the 3p state, 2 more in the 3s state, etc., etc. So you might have seen something like that if you've taken a chemistry course. One more thing I'd like to mention, and that is we have talked about these transition states, transitions, an electron going from a higher energy to a lower energy state. But we haven't talked about when that might occur or what might cause that to occur. I want to talk about one more thing before we finish. Let's imagine we've got an atom with an electron in a higher energy state. And we've been looking at it dropping down to a lower energy state. Now my question is, when might an electron in a higher energy state drop down to a lower state? Well, there are typically two processes that can occur. One is that it might just drop down just randomly. For no apparent reason, it just drops down from a higher state to a lower state. This is called spontaneous emission. So this photon is emitted just spontaneously. Now, we can't be sure when that will happen, but by understanding the structure of the atom, we can determine some probabilities. We can say what the probability is that the electron might drop down. But there's another method, and that's called stimulated emission. Now, what might cause an electron to emit by stimulated emission? Well, if we stimulate this electron with another photon. In other words, if we hit that electron with another photon with the same frequency as the photon that it would emit, we stimulate that electron to drop down and emit another photon. Along with the initial photon, we now have two photons. Now, this second emitted photon is in the same direction and with the same phase and polarization as the stimulating photon. This is a very interesting result. By sending in one photon, we end up getting two photons out. What we've done is we've taken this incoming radiation and we've amplified it. So we've amplified it using stimulated emission. Well, what is that? Well, that is light amplification by the stimulated emission of radiation, which is a laser. So that's how a laser works. A laser works by having a whole bunch of atoms with their electrons in a higher energy level, and then if you can stimulate them by these other photons, you'll end up getting two out, and then those can stimulate two more atoms, which then give you four photons, which can stimulate four more and get 8, and then 16, 32, etc., etc. So they increase by using this stimulated emission because the emitted photon is always in the same direction with the same polarization and phase as the stimulating photon. So let me give you a very basic idea structurally how a laser works. Here's a very simple structure of what a laser looks like. So first we've got this material in here, the material that does the lasing, so to speak. So this is our medium here. Now, the first thing we have to do is get those electrons up into a higher energy state. So we need some input of energy, and this energy is going to take those electrons in lower energy states and boost them up to higher energy states. They will then start to emit by spontaneous emission, and those photons will go everywhere. So we've got photons going all over the place. But occasionally we will get some photons in our axis, along our axis of our laser. If we get one of those photons to hit another atom, that will give us two photons in the same direction, which can hit two more atoms and give us four photons, etc., etc. Now, we'll have a mirror over on one end, say the back end here, and any photons that come this way will all be reflected back along the axis of our laser. And now remember, we're going to constantly have to have more energy put in, because as these emit spontaneously or by stimulated emission, we want to boost them back up to the higher energy level. So we constantly have to put energy into this. Now at this end, we could do one of two things. We might have a partially reflected mirror, which will allow some of these photons to come out and reflect some of the others. This will give us a steady beam of laser light coming out this end, and this is what we call a continuous laser. This is the kind of laser you usually see if you've got like a laser pointer or the lasers that we were using before for our interference patterns. These are continuous lasers. However, sometimes it's very useful to have a very, very powerful, stronger laser, but something that might be on for a much shorter amount of time. In that case, we might have a very, very reflective surface here to keep those photons going back and forth, to get stronger and stronger and stronger. Then we open up an opening here and allow all of that laser light to come out all at once. That's what we then have, that's what we call a pulsed laser. So that will give us a very, very strong pulse of light, but then we've got to close it off again and let it build up to get more power in the light again. Okay, well, very, very good. I'm afraid that is all the time we have, not only for this lecture, but for 11-12 altogether. I hope you enjoyed it. I hope you continue with your studies in physics, and there are so many more advanced topics that you can go into. I hope you had a good time. Thanks for coming. Bye-bye.